When we first talked about the rate law, we said that there's three different factors that determine reaction rate, which is concentration,
catalyst, and temperature.
but when we actually write out the equation representing the rate law, it looks something like this, which is rate equals to a constant, the rate constant times concentration raised to some order. And so neither catalyst nor temperature are explicitly written in that equation. But we know that temperature and catalyst both affect reaction rate. So the question becomes, where are they in that equation? How come we only see concentration? Well, if you think about it, the only explanation that would make sense would then have to be that the rate constant must be somehow a function of both of those factors there, which is catalyst concentration
and temperature.
So in other words, we have to figure out how to write the rate constant itself as a function of
these two factors.
And that's what we're going to investigate in this section of Kinetics lecture. Now, this was actually done some time ago by a scientist called Arrhenius. You might remember him from Chem 11 when we discussed those electrolytes and non-electrolyte solutions. And you'll see later on in acids and bases, he's also another person who made important discoveries. So he's a really prolific scientist. One of the discoveries that he made was he measured the value of the rate constant as a function of temperature. So all he did was change the temperature of the reaction and then keep the concentration constant throughout the experiment and look at the rate of the reaction. And he found this relationship. So you can see that as you increase temperature, that rate also increases, but because rate is proportional to rate constant and concentration, and if the concentration is constant, then the rate must be changing because
the rate constant is changing.
And so if you look at the shape of that plot that follows the data point, it has an exponential form. And so he came up with this equation right here, which is that the rate constant is equal to A. This is a different A than the concentration A that we've used so far. So you can see that there's no brackets there. So this is just something we call the pre-exponential factor, times E, your natural exponent, to the power of negative EA over RT. R here actually is a quantity you're familiar with. It's the gas constant that we had used back in Chem 11, and T here is
the Kelvin temperature.
I'll just mention here, A we call the pre-exponential factor, EA
we call the activation energy. We're going to discuss the physical importance of A and EA later on, but right now we're just going to discuss the mathematical use of the Arrhenius equation.
This is the exponential form of Arrhenius equation. You can also write the linear form, which looks like this. ln of k, again that's the rate constant, equals to negative EA over RT plus ln of A. There's an assignment that asks you to do that conversion from this form to the linear form right here. You can rearrange it if you have exactly two data points, meaning that you have rate constant 1 or K1 when you're doing the experiment at temperature 1, and you have rate constant 2 when you're doing the experiment at temperature 2. You can rewrite the Arrhenius equation into something I call the two-point form of the Arrhenius equation.
So let me show you how to derive that two-point form of the Arrhenius equation using the linear form of the Arrhenius equation, which is shown right here. Now, if we have two data points, as I said, we're going to have rate constant value 1 or K1 at the first temperature, or T1, and then rate constant 2 at temperature 2. Now, once we have those two data points, we can plug that into the linear form of the equation. So ln of K1 is going to be equal to negative EA over R, 1 over T1 in this case, plus ln of A, and then ln of K2 is just the same, but then now with 1 over T2 plus ln of A. Now, the EA over R quantities and the ln of A don't change. That's the reason is because the only thing that the temperature changes is the rate constant. So the actual activation energy and the pre-exponential factor, those two things are constant. Now, once you have these two equations, in algebra, you can just subtract one from the other one. And so if I do that, I get ln of K1 minus ln of K2 on the left side. And the right side, ln A will just cancel away because I have plus ln A minus ln A. And then what I can do is just factor out the negative EA over R and then put in parentheses 1 over T1 minus 1 over T2. Hopefully that makes sense. And then we can combine the ln K1 minus ln K2 and express it as ln K1 over K2. That's a log property. If we bring the negative to the left side, that would flip the ratio in the log expression, because remember that if you raise something to the negative power, it is the reciprocal. So now we have ln of k2 over k1, and on the right side is just a positive number. It's EA over R, 1 over T1 minus 1 over T2. And this is exactly that equation that you saw earlier, which you can see here. All right.
Right now, I just want to show you how to use the Arrhenius equation to actually calculate the activation energy and the pre-exponential factor. So we're going to do this example and apply the Arrhenius equation on solving this problem.
In this case, we have the data that's basically the same as what Arrhenius did. The experiment was done at different values of temperature, and you get different values of rate constant as a result. They're asking us to do a couple of things: calculate the activation energy. Remember, that's the A in that equation, and then the value of the rate constant at 430 Kelvin. Okay, so there's a better way and sort of like not so good way. So the not so good way is to just take this formula and pick any 2 points in the experiment. So for example, you can pick the first two, you can pick the last two, you can pick the first and the fourth, whatever, and then plug it into this 2-point form and then solve for the EA. Okay, so you could do it that way. That wouldn't be so good as this method that I chose to do, which is to plot it. So I can plot it because this equation is a linear equation, right? So remember that linear equation has the form of y equals mx plus b, and I could see it that this is ln k equals a negative EA over r 1 over t plus ln of a. So in other words, if I were to plot ln of k as my y-axis and 1 over t as my x-axis, I should get a line, downward sloping line, a negative slope line, and the slope of that line is going to be equal to negative EA over R. So what I'm going to do here is plot the data and get my information using the slope of the line as I just mentioned. And we have to make sure that we plot the right thing because the linear equation looks like this. And so our y-axis is actually ln of k and our x-axis is 1 over t. So we have to plot those. I'm going to use Microsoft Excel to help me calculate those values. So I'm going to, in Excel, create 2 columns, one of which is going to be my x-axis. So that's going to be 1 over temperature. This is in inverse Kelvin. Okay, just keep that in mind. We have to change it to Kelvin first and then take the inverse. And then the y-axis is going to be the natural log of the rate constant values that are given in that table. Once you do that, you're going to get 4 points, since we have 4 points in the original data. And then all you need to do is then fit it with your straight line. Once you get that, you ask Excel to give you an equation. You can see that that's the equation. So the actual slope here is negative 19,038. And of course, the unit here is the unit of y over the unit of x. Since the unit of y is nothing, since we have natural log, that's a unitless quantity. The 1 over t, if you put that in the denominator, then it just becomes Kelvin, okay? So that's the unit of slope. Now, of course, that's equal to, in our linear equation, that quantity is equal to negative EA over R. And then so EA itself is going to be, with the negatives cancel out, just 19,038 times R. R is going to be 8.314. Remember, this is a unit Kelvin. This is joules per mole Kelvin. So the Kelvins actually cancel away, and then what you end up getting in the end is just going to be joules per mole. And it's actually a pretty big number, and this is typical for activation energy. So a lot of times we just express it as kilojoules. So in this case, it's going to be 158 kilojoules. Now you can put more significant figures if you want, but right now I'm just going to limit it to 3 sig figs. Once you have the EA, it's pretty easy to then use the information to calculate the value of the rate constant at 430 Kelvin. You can plug it into your 2-form equation if you want, or you can just use the plot and then extend the value, right? Remember that this is really a relationship between ln of k and 1 over t. So if you know the temperature, you have the actual equation, you're trying to solve for k, you can just plug those numbers in with the new temperature, and then you can solve for your new rate constant. I had said earlier that this method of plotting is better than using the 2-point formula to calculate your answer for part A for the activation energy. And the reason is that if we pick these 2 numbers here to use in our 2-point formula versus, let's say, picking up these 2 numbers, or picking up the first and the fourth, or picking up the first and the third, you can see that depending on which values we pick, we're actually going to get different activation energy values every time. And that's always a point to remember, that when you have data, you want to use all your data. You don't want to pick and choose 1 or 2 of your data. You want to use the entire set of data, because that would give you the most reliable model of the entire set of data that you collect.